This is your lesson for 5.1, Extreme Values of Functions, and this will most likely be part 1. Part 1 has a lot of vocabulary and definitions, so I thought it would be acceptable for me to not have to appear in the frame because there isn't a whole lot to work out. And then the second part video will have a lot of example problems for us to work through. So extreme values of functions, we're going to be talking maxes, we're going to be talking mins, but we are going to be distinguishing between absolute maximums and minimums and what we call relative maximums and minimums. So this first little thing that we have here, it says you have let f be some function with domain D, then f of c is going to be your absolute maximum if and only if, remember that IFF means if and only if, all the f of x's are less than or equal to the value of f of c. So f of c is going to be, if all the other f of x's, so I have all these black f of x's here, if those are all lower values than what f of c is, then f of c has to be the absolute maximum. That means that there is no other value that is greater on whatever interval you're looking at. Then for the minimum, it's going to be the same thing, except for the f of c is going to be lower. So you'd have these other f of x's floating around here, but f of c is going to be the lowest point. And that's for all x in your domain D. Instead of absolute, sometimes this will be called global. So just know that global, absolute, those are interchangeable words. Okay, so we have the first example here. And I kind of went through and drew this out and worked this out so you can kind of see what it looks like. We have the interval negative pi over 2 to pi over 2. And it says f of x equals cosine. It's going to take on a maximum value of 1 once. So that's the blue equation that's right here, and a minimum value of 0 twice. That's at negative pi over 2 and pi over 2. What are the maximum and minimum values of g of x is equal to sine of x on the same interval? So the red line here, that is sine. So sine's maximum is going to also be 1. That occurs once at pi over 2. And the minimum is negative 1, and that occurs once at negative pi over 2. Remember one of your lessons from Algebra 2, and I'm sure you did this in trig last year as well. When you are identifying the maximum or minimum value, you always state the y value, and then the location of the max or min is at the x. So you'd have the max of y at the x, and you'll see that once we actually get into some of the examples for today. In your book on page 194, there is an example I want you to go through and look at. This goes through how you can change the domain to change the answer of what your mins and maxes are. This would be whether endpoints are included or not included, or whether you're including the entire domain of the function or you're restricting the domain between certain x values. So you can actually change what you're going to have for your maxes and mins depending on what your domain values actually are. Now we get into some of the theorems. So this first one is called the extreme value theorem. So you have, if f is some continuous function on a closed interval a to b, then f has to have both the max and a min value on that interval. So no matter what function you're looking at, if it is continuous on a closed interval, that means there's no breaks, there's no holes, there's no jumps, there's no gaps, and the interval is closed, so the endpoints are both solid dots, then you have to have both a max and a min value. You might have the max occurring at multiple places or the min occurring at multiple places, but there has to be a max and a min value. And 194 offers a little bit more of an explanation behind that. So moving on from absolutes, we have locals. So for your local extreme values, if we let c be some interior point in the domain of the function f, your f of c is going to be a local maximum if f of x, if and only if, remember again that IFF is if and only if the f of x's are less than or equal to f of c for all x in some open interval containing c. So the open interval could be something that's stated. It could be something that maybe you're just looking in that immediate area, but the f of c is the highest locally in that area. It doesn't have to be the highest overall, but in some area it is the highest. And then for the minimum value, f of c is going to be the lowest value in some local area. These are sometimes called relative extrema instead of local. So just like you had absolute and global, local and relative are also going to be interchangeable. And also, all absolute extrema are also called local. And the way I always describe this is, for example, if you think about track is always a good example for this. The person who runs the fastest, 200 meters in the state is local somewhere. So even though they're the absolute fastest in the state, they're still going to be the absolute fastest locally. Whereas the person who's the absolute fastest locally isn't necessarily going to be the fastest in the entire state. So that's why all absolutes are local, but not all locals are absolute. It just depends on the problem. So now we have theorem 2, and this one is extremely important. This is going to kind of drive our math that we're going to use to solve for these local extreme values. If your function has a local max or a local min value at some interior point C of its domain, and the derivative exists, so it has to be differentiable wherever C is, then f prime of C is equal to 0. So if we know it has a local max or min, then the derivative at that point would have to be equal to 0. If the derivative at that point is equal to 0, that doesn't necessarily mean that it's a local max or min. You have to do a little bit more testing to figure out if that's actually true. Okay, so now a few definitions and a few important things. The critical point and stationary point, there's actually only one difference between these. And typically on the AP exam, you won't see much said about stationary points. Really, they're only concerned about critical points. So your critical points are going to be the points in the interior domain where f prime of 0, or f prime is equal to 0, or f prime does not exist. Because even though you have those places, for example, like a cusp or a corner, where you can't actually go through and take the derivative there, that doesn't necessarily mean it's not still a critical point, because it still could be either relative or absolute max or min. So critical points do include places where the derivative doesn't exist. But more importantly, it's also the places where the derivative is equal to 0. Your extreme values can only occur at critical points. So if you have some point that's not a critical point, it's not possible for an extreme value to occur there. Stationary points are the points where your derivative is equal to 0. So stationary points are going to exclude those places where the derivative does not exist. And as I said, you won't really see much distinguishing between them. Typically, we only talk about critical points and not stationary points. Stationary points, they could be maxes or mins. Sometimes they're inflection points, which we'll talk about a little bit later on in chapter 5, but they're not necessarily the same as the critical point. Because again, there are critical points that are not stationary points, and that would be where your derivative does not exist. So that's going to bring us to the end of the first video. The second video will be going through some of the examples, and this is the first example I'm going to begin with. Go back through, read over this. You do have the book video available to you as well, and reach out to me if you have any questions.